showed in the O here. And there's a group of Japanese again. We found that this kind of material is so amazing. With the parent compound, all right, is the insulator, non-conducting at all. But when you insert some water between this cobalt layer, and then it becomes superconducting. Okay, you need water. All right. So this is amazing system. Anyway, so there are many, many interesting compounds show superconductivity after the past in the last 25 years. And a real surprise was came up is about 3 years ago in 2008. That's another story that nothing is impossible. As a Professor Hosono in Tokyo Institute of Technology, he reported there is a new compound with the iron as a key element. Okay, and based on the BCS theory or the old understanding of superconductivity, the iron component actually is no good for superconductor because it's magnetic. When you have something magnetic, it's not compatible with superconductivity. However, this paper showed that there is a superconductor with iron as the key element and TC around 26 Kelvin. Oh, so right after this discovery, many people immediately follow, especially a big group in China really made a great effort, okay? Well, at that time I was also working on, and so I immediately realized, at that time actually, in the original paper already showed that the superconductor should be coming from this iron arsenate, this layer, just like a copper oxide in the cuprate. And so we think that we should look at it. However, in our laboratory, it's very difficult to work on the arsen. It's a toxic material. You need a special treatment. So there's no way we can work on that. So we think, well, maybe we can find something else instead of using the arsen. If we can find something with this kind of structure, maybe we'll be able to find a new superconductor, okay? To make the story short, indeed, we found in literature is already exists the iron selenide, okay? That can be formed into this kind of hexagonal structure, which is magnetic, with the magnetic order about 130 Kelvin. However, if you manage to make it into a different structure, this tetragonal, then this material become, from magnetic-wise, it become very weak, the temperature dependent. Okay, so there is somehow the magnetic feature disappear. So we use this idea and start to work on that, and quickly, yeah, we did find a new compound we call the 1-1 structure, iron selenide, which is superconducting. TC is not that high, only 10 Kelvin. Okay, and I'll talk about this later. And about the same time, a German group find that you can make a superconductor by using this kind of so-called 1-2-2 composition. And this is the original Japanese group of Hosono's discovery. And another Chinese group in Academy of Science, and they found that can make it this was iron selenide, arsenate with a lithium insert called a 1-1-1. Okay, so that was middle of 2008, around May, June, and O4 system was already discovered. Okay, and that was another race. Okay, between the community on superconductivity. And this is how 2008, right? The thing reported. And by 2009, there are already so many systems, okay, discovered. Yeah, and that's why you can tell superconductivity, so why it's so important, okay? So because the excitement created every time you find something. And by 2009, already showed that the TC can be as high as 60 Kelvin. So people start to think about, can we break this and the barrier on this system? Well, but unfortunately, so far, there's still no such a sign. Right? However, this discovery does bring up something really important fundamentally, okay? So in the next couple of minutes, 10 minutes or so, I'll tell you what we think that's important for better understanding of superconductivity. So from the fundamental point of view. So this is, I'm going to use a system we discovered in 2008. This is a so-called 1-1 system. And look at that structure, it's so simple, right? It basically is a so-called infinite layer. You have iron as a point, then the selenium up and down form into a perfect tetragonal symmetry. Okay. And because of the structure is so simple, so anything you measure by look at the simple property like resistivity or other, you will see some feature. Okay, and I will show you. For example, this is the first resisted curve we obtained on this system. Just look at the temperature dependence. You see, there are two features. One here, right? This is not like a normal metal. Normal metal, you have almost linear, quite linear, and then drop. But here you see there's a sort of a bump, and there's a dip, a small change here. So you see something already. Right? And of course, we have asked us, what are those features? Okay. And of course, yeah, this is definitely coming from that layer here. So we measure again by using another method, measure the so-called thermal power, the thermoelectric, which is also a measurement, a technique to reveal the electron transport in the system, okay? And this is the sample we measure by cooling down. And you see that about 230, 40 degrees, there is a sign change from positive sign to negative. So indicates something going on here. Right? If you are solid state physicist or chemist, then you know some kind of a band crossover from one band to the other band. Right? And then another interesting feature is that around 100K, there is a maximum, if we look at the negative way, or the minimum here. This is the maximum in the thermal power. And then go back and then become eventually zero. That's the superconducting state, okay? And this two temperature, if you go back to look at the resistive curve, that is here and here, right? So this already tells us something. And then just for comparison, we believe there are some general feature for all the iron-based superconductor. And this is the data I got from my friend from China. It showed that the 1111 also there is some kind of maximum in thermal power. And even this is from Professor Chiu. They were looking at this 122 compound, which is superconductor. They also show that there is some maximum here. So something, this maximum thermal power will tell you something in this material. Okay. And in fact, more recently, there is this new discovery following our 1-1 system. A Chinese group also managed to make a 2-2. This kind of, we call it 1-2-2 with the selenium instead of the arsenic. And that also becomes superconducting. And the data also strongly show that only those which sample which are superconducting, then the thermal power will show this kind of behavior. For non-superconducting one, because you can change the composition and they become non-superconducting, and then that kind of feature disappear. So this maximum thermal power seems to be a very important feature for that. Okay, and what is this feature? Okay, so back again to this electrical, and we decide to really look into detail of the structure, and we found that actually this is all back to Dr. Banner's the original talk. There's the so-called similar Young-Taylor. This is the tetrahedron, right? May not be exactly Young-Taylor distortion, but there's a structure distortion that appear at around 100 Kelvin. Okay, so the system really going from originally is a square and somewhat stretched, and then you making this angle become larger than 90 degrees. Okay. And this is the feature that show all the key thing I just show you, the resistivity, thermal power. Okay, you know that no low temperature distortion, no superconductivity. Okay, this is our conclusion. And then we have to ask, why is this distortion, and what is this distortion lead to us? And this is what we are currently working on, try to understand from the more physical, understand from the physical property and to get a better understanding what's going on. Okay, and so we have done many work. This just quickly show you some of the data, like the Raman. There's probably some kind of phonomole has been changed at that temperature because of the distortion. And this is understandable because the structure is different at lower temperature. Okay? And we can use the NMR to look at some of the fundamental feature by looking at the dynamic of the electron, and it shows that there is a so-called spin fluctuation. Okay? And this is two different work. This is from our group. This is from a Canadian group working together with Princeton group in the United States. They also show that around the temperature, this signal from NMR goes up. Okay, it's like this, and that's indicating the spin. It all used to be can be older now because of this change. It becomes sort of disorder or fluctuate out. So no more spin order. Okay, and I collaborate with somebody in Canada by using the so-called muon spin rotation. They also support that there is a 100-degree Kelvin spin fluctuation showed up. Well, more recently, actually, we are using a very interesting and sort of powerful technique by looking at the so-called femtosecond optical pump flow. This is also a little bit detailed, but I want to just show you that usually this technique will give you several features. One is look at the acoustic response. And we don't see much from the acoustic part, meaning that the lattice only show the stiffness, because when you go at a lower temperature, the lattice doesn't vibrate that easily. So it's 比较硬一点, so the stiffness, and that's conventional, you don't see that. But from the electron dynamic point of view, that is very interesting, okay? So this is the data for electron, and we found there, by fitting the data, okay, then you can use the two kind of parameter. One is this linear part, and then another the exponential part. Means that there is a short time response and the fast time response, and you can see two features there. Right. And the data indicate for the short electron or the relative slow electrons to respond. Well, there's a crossover about the same temperature there, okay? The phase response at the 100 Kelvin, then there's the relaxation time different. Okay, this is the electron, the response to the optical energy, okay? And there's a very fast response, and then there's a sudden change. So all this indicated this 100-degree Kelvin fundamentally very important to the distortion and give you a lot of interesting in terms of electronic change, and that also related to the spin structure of the system. Okay? And that's, what this kind of two process, we need to understand this kind of dynamic, okay? And as I mentioned, this AO is the slow dynamic, and that this indicate there is another temperature dependence of the thermal reflection signal, and that is the recombination of the photocarrier. And so the structure change really give you a very important the phase dynamic difference here. Okay. But unfortunately, until now, we still don't have a full insight because we need to have a better, some kind of a band structure. The crystal, we know the crystal structure, but there is no electronic structure so far. There is no party really looking at from the theoretical point of view. I have been asking my theory prep friend to do some calculation. So far, I have not got any data. Okay, so we are still waiting for some information to understand. So here is the message based on this. Apparently, a structure change at 100 Kelvin, and that lead to many interesting electronic property change, and also the spin part. And this really is the key to go to the superconductivity. And that's, it's not only for the iron selenide, you know, with the lower TC. Obviously for the other system, we believe has the same feature, okay? But why we have this distortion? Well, we further look into this high temperature part again. As I mentioned, there's a crossover from the band cross, right? And this is the Seebeck coefficient at the high temperature. So we start to look at whether there's some other feature. A simple way is to look at study the magnetic property. Okay? Without going through detail, we also show that, okay, we can look at the crystal in different orientation. This is the crystal. And you can measure the magnetic along this or perpendicular. And you see a very strong anisotropy between two direction orientation, okay? Which means this iron and selenium, you have a d orbital, like a copper oxide, and oxygen, you have a p orbital. And here you have a d and p orbital, and somewhat that kind of an orbital effect, okay, become essential. And you sort of indicate maybe there are two kind of electron. This can spin orbital coupling. You have some itinerant, some more localized, and that's how your spin fluctuate. And also give you to this 100-degree Kelvin distortion, okay? So this is the, sort of based on the data, we speculate that. And from the fluctuation and get to superconductivity, okay? So this is what's going on recently for the last 3 years, very important from scientific point of view. Okay. Of course, I think this is exciting for superconductivity because we may find a potential direction that we can better understand of those, or this so-called normal superconductor. Okay. So what I just talked to you, from the iron, from the copper oxide to the iron based superconductor, there are many things going on, okay? But which is good for the young people like you because it has a lot of challenge, opportunity for you to explore, right? Especially like this, where I think we need to revisit the copper oxide system to see whether there are also exists such a structural property correlation, okay? Yeah. It was indicated that early day, but somewhat because of all the different way of thinking and this kind of structure and property correlation seem to be forgotten, okay? But I think this is the kind of a message I want to bring to the audience. There are great opportunity for you to explore for the superconductivity. Earlier, Dr. Bano told us that for technology development point of view, we have many opportunity and many challenges we have to accomplish, and which will be important for the humanity. But on the other hand, scientifically, there are many things we can also really, worthwhile to put the effort and look at. And the final view grade is just for entertaining, all right? For you to entertain. It is a guess. Which is interesting. Let's look at compare two culture or two feature. Is the evolution of a civilization and the evolution of superconductivity. Okay, let's look at the timeline. Well, people, the humans, civilization started with this tool, right? We used stone to make our tool, to use it as a tool. 就新石器时代，我们开始有工具 right? So that was about 10,000 BC. Okay, if you look from the history. And then after 7,000 years, you go to the so-called Bronze Age. Right? This is using the copper as a major tool. Then the 3,000 BC, that's the 7,000 years. And then the Iron Age started around 1,000, which is the 2,000 years after the Bronze Age. Right? All right, let's look at the superconductivity. It started out with 1911 with 4 Kelvin, and almost 75 years, or the equivalent of 7 hours, but divided by 100. Right? So it's actually 2 years, 100. So 70 years, then you got to copper oxide, the copper, the bronze. And then 20 years later, the Iron Age comes. Okay, the iron superconductor. So this is the 2000. Again, divide by 100, then you get this time. Do you see the point? So there's the equivalent of the, and we know today that we call us at the silicon age, right? Because everything, semiconductor, every tool or every gadget we are using, iPhone, iPad, everything, are all basically using the silicon, even the solar cell. And that take about 3,000 years. Right? So maybe 30 years from now, we have a new superconductor. Right? Well, this is just for entertainment, as I said. You don't take it too serious, but it could be something, because something in silicon maybe something you want to look at. All right. And maybe there are some future. If you look at carefully what we learned from the copper oxide and the iron-based superconductor, from the structure, that's why the chemists and physicists really need to work together, because chemists know how to manipulate the material, and the physics will manipulate how to understand the property. And if we can work together and understand all this, well, I guess by the time we should be able to get a much better. And the temperature can be higher, right? Because it's sort of, we go back to the stone. Silicon is just like a stone. Right? So we are back to stone. And stone, and if you look at it, the iron is only a lower temperature than the copper. And you go back, the temperature will be much higher. Okay, you see what my implication? If we go back to the stone, and then this is the lower temperature, higher, and then go back to really high temperature. The room temperature will be achieved by then. All right, so I guess that's all I want to say. And I guess if we have to work together and work hard enough, then we should be able to advance more and more. Thank you very much.
Thank you, Dr. Wu, for your wonderful lecture. 接下来为提问时间，现在将时间交给陈颖干教授。
I think there's many audience in our either high school or undergraduate and or graduate students, and I think they very admire your achievement in scientific career, and I think they were very interested to know, or you can share some of your experience in their early stage, how you feel, and if they are interested to pursue a research career or something like that. Can you share some of your advice or something like that?
I'm not quite sure whether I understood your demand correctly, but apparently you are encouraging me to give some advice to young students. Is this correct? Okay. Well, I'm frequently asked about advice. Well, I can only describe how I try to master my scientific career. Well, certainly this was not going smoothly all the time. During my studies at the university in Germany, we had to do examinations, and it happened from time to time that I did not perform very well. And this is quite usual. But what I learned is that you don't need to regard this as a disaster if you have a failure once. I think the most important thing is that you learn from failure, from mistakes, and try to not to do it a second time. And if you fail in examination, you try again, and you should learn first of all what was missing, and then you concentrate on getting these mistakes straightened out. During my time at the IBM Research Laboratory, when I joined the research laboratory as a young scientist after my PhD, I was slowly driven into an activity which I started to dislike. And at that point, I decided either I continue my career at IBM on a different project, or I have to leave. I have to make a firm decision. If I don't like this work, I don't continue. And then you have to make a very hard decision. I guess this is something which through all my career, I took as a guideline. Even after the Nobel Prize, there were situations where I didn't feel comfortable, and I decided, no, everybody is expecting something from me, but my personal decision is I don't do it. If I don't like it, I don't do it. And well, on my office, as an example, I had a sign telling what part of no don't you understand. Sometimes it's hard, but it's needed that you tell yourself no or tell somebody else no.